Namaskara. We continue our discussions on the basics of walks and paths and move on to describe the shortest path problem and then derive certain important mathematical properties of the parameters that we are looking for. Okay. The shortest walk, the weight of a shortest walk can be reduced to minus infinity if there is a negative cycle in the walk. You can move around that negative cycle again and again, keep reducing the weight of the walk and you can make it to minus infinity. Okay. If there is no negative cycle, then shortest path and shortest walk are one and the same. Okay. We will make these kind of observations now. First, let us note that if W is a walk from U to V, then W contains a path from U to V. It is a subset of edges. What is the definition of a path? No repetition of vertices. A walk may have repetition of a vertex. Repetition of a vertex means you start from a vertex, you go through various edges and then again come back to that vertex. So, there is a cycle of edges that are defined between two successive occurrence of a repeating vertex. Remove all of them. When you remove them, one repetition is removed because you have removed that cycle of edges. It is still a walk, the other parts are intact. In other words, if I have a cycle, because this is a vertex that is repeating, this is the first occurrence and then the second occurrence. Between the two successive occurrences there are a lot of edges. These edges will form a cycle, okay, between the first occurrence and the next occurrence. Remove them. So, when you remove them you get still a walk. So, whenever there is a repetition, there is a cycle of edges between the two successive copies of the repeated vertex. Remove those cycles. When you keep removing them, all the duplicates are removed. So, this process will lead to a path. Okay. So, if W is a walk from U to V, then W contains a path. How to obtain that path? We obtain the path by removing the cycles from the walk. Keep removing the cycles, that will keep removing the duplicates. Finally, you will have a connection from U to V with no duplicates and that is actually the path, right. So, this is the important property, we must remember this. We also see that now if G has no negative cycles, assume that G has no negative cycles. Let W be a path from W be a walk U to V. Assume that G has no negative cycles and let W be a walk from U to V, then W contains a path P from U to V such that weight of a path is less than or equal to weight of the walk. Why this is so? It is simple. The graph has got no negative cycles. So, all the cycles that you remove are either 0 cycles or positive cycles. Removing 0 cycle does not change the weight. Removing positive cycle reduces the weight. Therefore, the path P you have got by the removal of the cycles will have either equal weight or a smaller weight, and that is what is stated here. The path that you find in the walk, it is a subset of edges, it forms a path. The weight of that path will be less than or equal to weight of W. That is because the cycles that you are removing from the walk to get the path P are all either 0 cycle or positive cycle. Very important property. So, you can call this as property 1. You can call this as property 2. We will also make another observation, interesting property. So, a walk, if you look into a graph that has no negative cycles, the shortest walk will be a shortest path. That is the important property 3. If G has no negative cycle, then the shortest walk from U to V will be a shortest path from U to V. Okay. If G has no negative cycles, we will also assume that G has no 0 cycle, because 0 cycles, the edges of 0 cycles can be removed without changing the weight. By removing all the edges of a 0 cycle, the weight is reduced by 0, which means the weight is not altered. So, we can assume that no zero cycle also. If G has no negative cycle and no zero cycle, then the shortest path will indeed be a shortest walk. Can the shortest walk have any repetition of vertices? In other words, can it contain a cycle? Okay. How do we prove this? Proof for property 3. If the shortest walk has any cycles, any cycle, it can be removed and a shorter walk is obtained. If the shortest walk has any cycle, I can remove that cycle. The cycle has positive weight. This is because the weight of the cycle is positive. There is no zero cycle, there is no negative cycle. So, if at all there is a cycle, it will have a positive weight. So, if I have a walk like this and if I have a walk like this without that cycle, it will be smaller in weight, right. Therefore, the shortest walk cannot be shortened further. By definition, that is the shortest. How can you reduce the, if there is a cycle, it can be reduced. Since it is not possible to reduce, there are no cycles, there are no repetition. Okay. This contradiction shows that shortest walk cannot contain any cycle. That means shortest walk is indeed a shortest path. This is possible only, right, when the graph has got no negative or zero cycle. If the graph has got no negative or zero cycles, then the shortest walk will indeed be a shortest path. Hence, if G has no negative or zero cycle, then alpha uv equal to delta uv. Shortest walk is same as the shortest path. It is indeed a path. Only if G has no negative cycle. If G has negative cycle, well, things could become different. Okay. For example, if I have A, again take this simple example of this 5, 10, 5 minus 10. The example we have seen already. There is only one path from A to E. A, B, C, D, E. That path is A to B to C to E. This is the path, only path. This is the only one path. Therefore, that is the shortest path. Its weight delta AE is 5 plus 10 plus 5, 20. But we have seen that alpha AE is minus infinity. They are different. Alpha UV equal to delta UV only if G has no negative cycle. If G has a negative cycle, this example shows while delta is well defined, alpha could become minus infinity. Okay. Since every path is a walk, set of all paths from U to V, it will be smaller than set of all walks from U to V. It is a bigger set. Every path is a walk, but there are walks that are not paths, therefore it is a bigger set. Minimum over bigger set will be smaller. Alpha UV is less than or equal to delta. If you have a bigger set, superset, minimum of a superset will be either smaller or equal to the minimum of the subset. Okay. So these properties are all very useful in the design as well as the proof of correctness of algorithms. With this, I conclude this part. We will discuss about the mathematical foundations and basic properties of shortest path weights in the next session. Thank you.